So today's lecture is on constrained and non-convex optimization. So in our last lecture, we saw how to do optimization. And remember that optimization is about minimization, maximization, and root finding. So we're going to tackle non-convex optimization. So last time we saw what is a convex optimization, what is non-convex optimization. We'll see one approach for non-convex optimization. And then we're going to look at adding bounds and constraints. So non-convex optimization is not really a solved problem. So minimization, convex minimization, and root finding are relatively solved problems, but non-convex optimization is an open problem. So SciPy has a method called basin hopping, which is kind of like a Markov chain or a Monte Carlo optimization. It's okay. There's actually been some nice improvements in the last year or so, and there's now four different non-convex optimizations in SciPy Optimize that look very promising. And so like this is an open area of mathematics, so things are changing constantly, and so SciPy Optimize has a few options here. So it's nice to see that the progress in the mathematics field is being translated to Python. But we will basically use basin hopping in this class because it's a relatively simple method and it's the most common in SciPy versions. So let's remind ourselves of what a non-convex function looks like. Here's an example of a non-convex function. We can identify it's non-convex because it has multiple local minima and obviously only one global minima. It's essentially, this function is a cosine with a parabola added to it. So it's just like a parabola that has kind of a rough surface to it. So if we use basin hopping, it looks like this. Now the difference between convex and non-convex is that it never knows when to terminate, right? It never knows, like looking at this function, it never knows if it's at the global minima or a local minima. So you actually have to just tell it how many iterations to run for. So we have our same thing that we did before, where we tell it what is the function we're trying to minimize, what is the starting point, and then now we have to add in how long to run it. And again, we get sort of a complicated result. So we have sort of what we saw before of like, the Hessian, the Jacobian, the message, things like that. But we also have some extra information down here. And this tells us about the basin hopping. So the way basin hopping works is that it kind of wraps up the other minimization functions. So it does minimization. That's where this top message comes from. It comes from the BFGS minimization algorithm. And then these bottom ones here are coming from the basin hopping method. So it says, here's the message that it did the number of iterations. Notice it will never say like optimization terminated successfully. That's up here. This is from the inner local minimization method, but the basin hopping, it never says it completed successfully because there's never a way to know for sure that you've found all the local minima. And then it gives you obviously the x value here and here, and the function value. So if we look back on the function, it found this point here, which is indeed the global minimum. And so one of the things I'm going to do in this lecture is plot little red dots showing the global minima. The way I do that is I call plot, and I just give it the x value and the value of the function that was returned. And then I make a red point there, so that just shows you where it found it. So that's all we're going to look at for now with basin hopping. Essentially, all you do is you call basin hopping, and then you just add an n iter on top of it. Now, one thing about it, we'll see this in more detail later on, is that if you want to change how basin hopping calls the minimize, so basin hopping calls minimize for you on a bunch of different spots. So if you want to pass arguments to minimize, which we will see is necessary for constrained and bounded optimization, we pass in a dictionary, and that corresponds to the arguments we want to pass to the minimizer. So are there any questions on basin hopping, the method that we use in the class for non-convex minimization? Okay.
I have a question.
Yep.
I wonder, like, what's the mechanism of basin hopping? Is it like the Newton's way? Newton's way?
Well, okay. So Bayesian hopping is a combination of local minimization and global minimization. It does the BFGS minimization locally. It's like if you're here in Bayesian hopping, what it will do is it will use the BFGS optimizer to find a local minimum. So like if it was here, it would find this local minima here. And then it does kind of a global step. And then what it will do is it will just basically randomly choose a point far away and switch to doing local minimization in that other point. So it will basically be here, then it will randomly jump over here, then it will randomly jump over here. So the name basin hopping is that it's hopping between basins. And the way it hops between basins is with something called Metropolis-Hastings criteria, which is a type of it's like an annealing or it's like a quantum tunneling kind of thing, where you randomly will go to a worse spot. And how often you randomly go to a worse spot is controlled by something called a pseudo temperature or temperature. So it's just kind of like hopping between the local optimization basins. So on the inside, like when it's in a basin, it uses just the BFGS or Newton optimization methods, or not Newton. I don't think it would use Newton. It would use I forget the name. Maybe it does use Newton. And then outside of it, it will do this kind of Metropolis-Hastings criteria to hop between the basins. Any other
Thank you,
questions?
Professor.
Yeah. Okay. So the moving on from non-convex optimization, sometimes we want to restrict our bounds, and restricting bounds is done differently for root finding and minimization. Okay. And one of the things about SciPy is that there's not really a method for bounded root finding in n dimensions. I have to double check this year. This may have changed, but what we'll see is we can basically do bounded optimization or bounded minimization and then bounded root finding in one dimension. So let's start with one-dimensional root finding with bounds. So there's a method called BrentQ, and actually this is a pretty important method for chemical engineering because a lot of times we're looking at things like mole fractions, or we're looking at things like concentrations, and there we have bounds on them. And so if we want to solve an equation like a chemical reaction equilibria, and we want to solve it, we want to have bounds on our concentrations or molar ratios so that they're between 0 and 1. So what BrentQ will do is that you give it a function, just like all the methods we've seen, and then you give it two bounds, one on the left and one on the right. So remember, this is a one-dimensional method, so it needs to have a left and a right bound. So here we're finding the root for sine of x between minus pi halves and pi halves, and as you know, it's at 0. Sine of 0 is 0. Now, one of the restrictions on BrentQ's method is that the the two ends you choose, like here I choose this A and B, they can't just bracket it, like they can't just be the left and the right. It has to be that the signs are opposite. Okay, so why is that the case? Basically, for there to be a root in between A and B, one way to guarantee the root is that if A gives you a negative value and B gives you a positive value, the function must cross 0. Or if A gives you a positive value and B gives you a negative value, the function must cross 0. So that's a requirement to use the BrentQ method, is that the f of A and f of B have to have opposite signs, so that it guarantees that the function will pass through 0. Now, obviously, that can be violated if you have a discontinuous function or a piecewise continuous function, but BrentQ and most of these optimization methods are not designed well for piecewise functions. And Brent's method has to be convex, obviously. Otherwise, if you have a function crossing 0 multiple times in between A and B, then all bets are off. So here's an example of this. So if we have, sorry, this chat message here. Do Bayesian hoppings work like simulated annealing algorithms? Yes. So Bayesian hopping is like a simulated annealing. So simulated annealing is another example of using Metropolis-Hastings to do optimization. Okay, back to this example. So here I chose an A and a B, and notice that sine of A here is a positive number, sine of b is a positive number, so they don't have opposite signs, so we can't do root finding here. And it makes sense because there is no root between sine of 0.25 and sine of 0.5. The sine function does not cross 0. And then this is just showing the example again. So here we will see a real example from chemical equilibrium, chemical reaction equilibria. So before I go on though, does anyone have any questions about the setup here for this Brent-Q method? Okay. So let's say I have an acid dissolution. So I have an acid here, and it's going to its conjugate base. And I have water, and the water is taking 1 proton to become hydronium. And this is a weak acid, so there's some equilibria here. Maybe that should have an arrow going left and right. And let's say the equilibrium concentrate, or the equilibrium constant is 32.5. I guess it has units, 32.5 moles. So that means that if I take the products over the reactants, so I have here my acid times my conjugate base divided by the concentration of my acid. So we know from the mole balance that if the extent of the reaction to the proton, or the hydronium, is x, then we have to have the same amount on a molar basis of the conjugate base. And then the amount of acid left over should be 1 minus x. And this should equal 32.5. So I don't do chemical reaction equilibria that much in my daily life. So let me know, guys, if there's a mistake here or if you have any questions about this. All right. You guys covered this in chemistry, right? And OChem or something?
Yeah.
Okay. Can someone confirm that any of this makes sense to you?
Yeah, and like Gen Chem.
Yeah.
Okay, great. Thank you. Great. So, guys, it's hard to just, because nobody has their cameras on or anything, so it's hard to, know if everyone's following along here. So I can rearrange this equation to be root finding, right? Now, why can't I just take a square root here and do something like that? It's because this function has multiple roots. Like there's multiple places this will equal 0. So we don't want to start trying to reduce powers of x or do anything like that. So we leave it like this here. And now this is root finding, so we can use a root finding method. Now we can't just go use like the root method like we saw before, or Newton's method like we saw before. We need to use a bounded root finding method because x can only be between 0 and 1, right? So here I set up the Python. So I basically define Q here, and Q is the extent of the reaction. And then I define my objective function, and that is just Q minus K. Okay, so this is extent of reaction, and then obviously to get the root finding, I need to have Q minus K equals 0. Then I plug that in here. And then I start at, just as an example, I'm just showing you guys the wrong way to do it here. If I use root, so it's unbounded, and I start at x not equals 0, it tells me the extent of my reaction is minus 33, right? So my extent is between 0 and 1, right? And now it's to minus 33, so that is not correct. So then let's use Brent Q, right? So we use Brent Q, and then we put in our bounds to be between 0 and 1, right? Like those are the natural bounds. Just a moment. Sorry, my dog wanted in. So those are the natural bounds here, but the problem is that Brent Q starts by evaluating your function on the left and the right. So when you evaluate x equals 1, so if you look back in your equation, if you evaluate x equals 1, that gives you a divide by 0. So using bounded optimization between 0 and 1 is not correct. So what we do is we go between 0 and a number very close but not quite exactly 1. So I did 1 minus 10 to the minus 9. So it's like 0.999999999. Then if you do that, you get the correct answer, which is that the extent of the reaction is 0.971. So that at equilibrium, the concentration of the acid is 0.03 molar. Okay, so are there any questions on this example? So you can see like a couple things went wrong. One of the things that went wrong is the first time I did it, I didn't bound it. That's really important in this problem setup because we're talking about a number which can only go from 0 to 1. Then the second issue that happened is that my bounds, just like my starting point, if you recall in minimization, we could have problems where our starting point is not in the domain of the function. One of my bounds was not in the domain of the function. You can't have x equals 1. So I had to change that a little bit. Okay, so this example here, this is much closer to like what you will do in your junior and senior level courses where, yes, you know how to minimize and you know how to do constraints or bounds, but you need to choose the right method for the problem, and it requires a little bit of thinking about your equations. Okay, so now let's take a look at minimization. So that was root finding, right? We were trying to solve an equation. Let's now try to minimize a function. So let's try to minimize sine of x on the interval minus pi to pi. So the method we use for this is called sequential least squares programming. Okay, so this is a bounded minimization, and it also can do constrained minimization, but right now we're looking at bounds. So the way that we do the bounds is that we pass in a named keyword argument called bounds, and it takes in a list of tuples. Okay. Now, why is it a list? It's a list because this works in n dimensions. So we could have multiple sets of bounds, one for each variable. Now, it's a tuple because the tuple has the lower bound and the upper bound, right? So we have a list, one for each variable or each dimension of x, and then within each of those we have a tuple, and the tuple goes from minus pi to pi. Okay, so then it turns out that the minimum for sine of x on the interval from minus pi to pi is minus pi halves, which I believe gives minus 1 for the sine. Maybe it's minus pi halves, that's right. Okay, so notice that all we're doing is calling minimize, and to make it this sequential least squares programming, we just pass in bounds. So normally minimize uses BFGS, but if we pass in bounds, it suddenly uses sequential least squares programming. Okay, so all you have to do is just do minimize like we had done before, but you just add a bounds argument. Let's see another example. So 2 dimensions. Let's say I want to minimize sine of x times cosine of y on the interval of minus pi to pi. So here's what it looks like when we're doing multi-dimensional minimization. Notice my function still takes in one argument, x, but then I slice it to get the first dimension. I slice it again to get the second dimension. My starting point needs to also be 2 dimensions because my problem is 2 dimensions. Then my bounds need to have 2 elements in the list, one for each dimension, and then within each dimension I have a tuple indicating the lower and the upper value. Okay, are there any questions on minimization in n dimensions with bounds? All right, feel free to use the chat too if you don't want to speak up. We're going to see, I think I'm going to skip over this problem because, well, I guess we can talk about it a little bit. So one of the things we don't cover in the class, but is actually probably the most common application of probability theory, is basically fitting probability distributions to data. So like we saw for the normal distribution that, we have in the normal distribution, we have those 2 parameters, the mean and the standard deviation in the normal distribution. And you may have inferred, or maybe you've realized by now, that the mean of the standard deviation of the normal distribution can be, you can find those by getting the sample mean and the sample standard deviation from a population. And then you can estimate those things as a normal distribution. But sometimes, like if you have a binomial distribution, you might be wondering, if I have some data for a binomial distribution, how can I estimate the probability of success? Is it just the frequency of success divided by the number of trials? So that could be something you don't know, right? Or something you want to prove. And one of the ways to do that is with maximum entropy methods. So I'm just gonna, I won't go too deep into this example, but essentially what we're doing here is that we want to maximize entropy. So it's a maximization problem. Okay, so this is the definition of entropy. So entropy is a attribute of a probability distribution. So this pi is summed over sample space. And by the way, if any of you are wondering like, hey, what the heck is this? I thought entropy was a thermodynamic thing. It is. This is the same thing. If you take statistical thermodynamics, you will see that the definition of entropy is exactly the same in statistical thermodynamics as well as in probability theory. So entropy is an example of a functional. Entropy takes in a function like a probability distribution and gives out a value. So this is the equation for it. So essentially you look at all the probability values over your sample space, take their natural log and multiply them by their probability, then you sum them up. Now you may think this is actually the expected value of the natural log of the probability, something like that, but it doesn't quite work out that way because it's actually a function not of the sample, but it's a function of the probability. So it's kind of a weird quantity. Okay, so you don't need to think too much about it, but basically entropy here is something we want to maximize or minimize this sum. So this is something we want to maximize. That's what maximum entropy is. That's the goal. And this is going to be bounded minimization because this p here, right, if we're changing p, it needs to be between 0 and 1. So let's just see a quick example of this. Okay, so like let's say I want to compute this expression entropy. Well, what is the input to it? The input is going to be the probability, right? Then the output is going to be S. So if I assume that my P's are coming from a binomial distribution, so just assume my P's are coming from a binomial distribution, then that expression becomes this expression, or sorry, this is the definition of a binomial. So this is just me setting up a binomial distribution, nothing fancy going on here. Now here I'm going to compute negative entropy. Why am I computing negative entropy? Because I want to use the minimize method, and I want to maximize entropy, so I need to minimize the negative entropy. Right, because we only have methods in Python to do minimization. So we have to put minus signs in front of a quantity if we want to maximize it. So the input to this expression is parameters for a binomial distribution. So the input is parameters for a binomial distribution. So I have entropy, here I'm computing it. The input is going to be parameters for binomial distribution. Why is it parameters for binomial distribution, right? Because I set up here that it's like, what is the input here? It's a bunch of these probabilities. Well, it's in this example, I don't want to specify what is the probability of each element in the sample space. I'm just going to say this p sub I here is coming from a binomial. Okay, so each of these p sub i's is coming from a binomial. So I have a binomial that defines the probability at each point in space. Okay, I haven't told you yet why I'm maximizing entropy or anything, but just go with it for a little while here. So we have an input here, and that input is going to be x, and x is going to be the probability of success in the binomial distribution. I'm just fixing n equals 5 for this example. Okay, so then what I'm doing is I'm computing the sum of the probability over this space here. Okay, so what I'm saying is that if you give me a p, a probability of success, I can compute the entropy of that. Okay, so I'm computing the entropy of a particular distribution. So think about it this way: is you have this equation, and you can say, okay, with a binomial distribution with a probability of success of 0.2, what is the entropy? The entropy is 1.2. If you have a probability success of 0.5, what is the entropy? Well, I don't have it computed here, but I don't know. I guess it's maybe like I don't know, maybe 1.8. Then you can say, what is the entropy of a binomial distribution with a 0.9? Okay, and then whatever it is. Now, intuitively, you might think, okay, if we're using the word entropy, there might be some connection between how random or how spread out your distribution is and how much entropy it has, and that's true. Okay, and we'll see a picture example in a moment. But essentially, entropy measures how diffuse or spread out your distribution is. So then what does that mean for thermodynamics? In thermodynamics, entropy measures how spread out or diffuse your probability of states are, or how likely you are to find a particle in any one given spot. So the classic example for thermodynamics is that if you have a gas, right, you're in a room and you have a gas, and the gas all is like in one corner of the room and everywhere else is vacuum, that's a very low entropy situation, right? It's very ordered, it's very unusual. Whereas if the gas is sort of spread evenly throughout the room, that's a high entropy situation. That's a maximum entropy situation. So what does nature choose? What is it like if you go into a room with air in it? Well, usually the air is spread out in the room equally, not because of gravity, not because of pressure or anything like that. You can just make the argument of entropy that the air molecules should spread out, right? Because you get that result even for an ideal gas where the particles don't exert a pressure on one another. Okay, so back to our example. Essentially, all I have done is written out a function which takes in an argument, and that argument is the probability of success of a binomial, and it gives me the negative entropy of that. Then I can call the minimize of the negative entropy, which maximizes entropy, and I can put in the bounds. So I'm saying that, this argument here is a probability of success that can only go between 0 and 1. So I make it go between a very small number and a number very close to 1 to avoid any issues of like having a divide by 0. And it turns out that the maximum entropy binomial distribution is a binomial distribution with a probability of success of 0.5. That is the most entropically favored binomial distribution, the binomial distribution that assumes the least insightful binomial distribution, the one that has, maximizing disorder, is the one with a probability of success of 0.5. Okay, so are there any questions on this? Now, I know this is kind of a new idea to you guys about computing computing entropy of probability distributions, but are there any questions about that or about setting up the problem? Like, this is the actual setup, is that we wrote a function out, we set a starting point, and then we put bounds on it. So are there any questions on that? Okay, no questions. So if you're curious about entropy of binomial distributions, here's a plot of entropy of binomial distributions. Okay, so remember that each x value here represents an entire probability distribution. Like if I choose 0.2, that means I've made a binomial distribution, with a probability of success of 0.2. And if I choose a probability of success of 0.001, that's a binomial distribution with a very low probability of success. So this is the entropy measure of those different probability distributions. So if you're thinking about this from a thermodynamics point of view, you have different entropies for different ways you arrange particles. This is just gratuitous, this is not necessary for your learning, but this is just showing you like, right, so on this plot, each point corresponds to a binomial distribution. Here I've plotted every single binomial distribution. So like, for example, this blue one here, this is a very high probability of success. This blue one here is a very low probability of success. These red ones here are sort of middle of the road. And each one of these is colored by its entropy. So this red one here is a very high entropy, and the blue ones are cool, right? They're cold. They have very low entropy. This is just showing you like, different distributions have different entropy. So this idea of measuring entropy is very fascinating because although it's just some kind of mathematical construct, it turns out in nature, the distributions you come across all seem to maximize entropy. It's just how the universe works, is that, if you ever have a distribution in nature and, it could adopt multiple possible distributions, nature seems to choose always the one that maximizes entropy. And you can actually derive a lot of thermodynamics by just this assumption, by assuming that nature and the universe follows maximum entropy. Many results kind of just fall out from that. Okay, so that was a little diversion into entropy. And I think it's kind of an interesting diversion because maximizing entropy is actually a pretty common tactic in chemistry and chemical engineering. So it's an interesting application of minimization. So any questions on this example? Okay. So we just saw how to do one-dimensional bounded root finding, and we saw how to do multi-dimensional bounded minimization. And those approaches just allowed us to put constraints on where our x values were, like what is the domain of the function we're minimizing or root finding for. Now, constraints are much more arbitrary. Constraints define arbitrary equalities or inequalities that must be obeyed for it to be considered a solution. So let's say, for example, we have an x and a y, and we want them to only lie on a circle. Notice that you couldn't specify this by bounding the domain of x and y. Like you couldn't say x is between minus, pi and y is between minus pi and pi. No, the only way to specify this is with an equality constraint. So if we want to have x and y values which lie in a circle, then we have to write this out as a constraint equation. So this says, okay, I want you to do minimization or root finding, but I want you to obey this equation right here. So here's an example where let's say that I have x and y and I want them to obey this equation. And I want to then find a point on x and y. So these x and y have to obey the constraint that they sit on this circle. And I want to find a point on this circle that's as close as possible to the red dot. Okay, so this red dot is just something I chose, and I say I want to find what point on this circle is as close as possible to this red dot. That's the setup. Okay, so I have a constraint. I have to be on the circle, and I have a minimization. I want to minimize the distance between this red dot and my point xy. So I have two variables, x and y. They're constrained to be on the circle, and I want to find those x and y's that minimize the distance to the red point. So to set this problem up, I need to have a way to compute distance. So I define a distance function, and I test out my function. I recommend when you're doing any kind of optimization that you always test out the functions you're writing, because you want to make sure that, like we said, they take in, one argument, give out one argument. This one takes in two arguments, so I can't put this in to minimize, but I'm going to use it in another function. Okay. So I've defined distance, it works, it computes the distance between 2 points. Then I define my constraint equation. So my constraint equation is that you lie on this circle. So it's x squared plus y squared minus 1. Now the way we set up all constraints, do I say it in here? No. The way we set up all constraints for constraint minimization is that the equations all equal 0. So although my equation here is that x squared plus y squared equals 1, Python only will allow me to pass in constraints where they equal 0. So to rearrange my equation so that it has to be equal to 0, I just make it x squared plus y squared minus 1 equals 0. So that's the only way Python takes in constraints, is that they equal 0. So I rewrote this to be x squared plus y squared minus 1. Now this expression will equal 0 when I'm on my circle. Okay. Then I define my objective function, right? Like, what am I trying to minimize? I'm trying to minimize how close I am to that point. So I use my distance function. So here's my objective function. My distance function takes in the point, xy, and then it computes the distance from the point 3, 4, which is what I said, I wanted. And then I just test it out. This is just me testing out the function to make sure it works. Now to set up the constraint, we have to tell Python if it's an equality or an inequality. So the first thing I do is create a dictionary, and the dictionary has two keys. The first key is type, and I have to put the word EQ or ineq, depending on if it's an equality or an inequality. Then the second key in my dictionary is going to be fun, which is short for function, and I have to give in a function which takes in one argument and gives out one argument. And then Python will make sure this function is always equal to 0. Now, if I chose an ineq, an inequality, then this function is always going to be positive. That's what Python will do, is it'll make sure it's always positive. So there's only two type of constraints you can have. You can have either an equality to 0 or a positive inequality. So you need to rearrange your math to make sure that those are the two constraints you have. Then when I call minimize, I do the same thing. I give it my objective function, minimizing the distance to the point 3, 4. I pass in my starting point. Doesn't matter. I chose 0, 1 because that happens to lie on the circle. And then I pass in my constraint, which is this dictionary I just created. And then, it goes through and it computes it. And I'm plotting the result. So it turns out that this green point is the closest point that lies on the circle to the red dot. Okay. Phew. Okay, it's a lot of setup here for this problem, but I think the actual mechanics, just these two lines. This is the two lines that we're learning here is how to add constraints to calling minimize, and all the stuff above was just creating functions and making plots. So, are there any questions on this example?
I have a question.
Yeah.
Could you just re-explain the dictionary line of code?
Yeah. So to specify a constraint, I have to pass in a dictionary to minimize. And by the way, it could also be a list of dictionaries if you have multiple constraints. So to specify a constraint, it needs to be a dictionary, and the dictionary has two elements. The first element has a key of type. The second element has a key of fun. The first one tells Python if it's an equality by specifying EQ, or it contains ineq if you're saying that it's an inequality. And we'll see an example of an inequality in a little while. The second element, the fun element, needs to be the function for the constraint. So this circle was defined above here, and it's a function that gives me that x squared plus y squared minus 1. That's the equation that needs to be 0 to satisfy my constraint of lying on the circle. So does that answer your question, Jeremy?
Yeah, yeah. I wasn't sure if circle was like a keyword, but
Oh, yeah.
yeah, that makes sense.
Yeah, it was this function I defined right here. Good question. Are there any other questions on this example? Okay. So the method that is used here is LBFGS B. So I don't know what the L stands for. Maybe Legendre? No. What is that called when you have constrained optimization in calculus? Lagrange. Probably Lagrange BFGS. And I don't know what the B stands for. Okay. We did a lecture not too long ago on dictionaries, so I'm going to skip over this, but if you guys want to, you can look just to remind yourself of how Python dictionaries work. But here are the two types here. There's ineq and eq. So this just is just clarifying here. So like I did in the circle example, you have to make your constraints be equal to 0. And then for the inequalities, they're always going to be strictly positive. So like if your problem has this inequality, like your problem is set up to be, so in the setup of your problem, you need to have x squared minus 2y is greater than 4. You have to rearrange this into an equivalent inequality that's strictly positive. So if it's x squared minus 2y is greater than 4, you can make it x squared minus 2y minus 4 is greater than 0. So now we have an equality that's strictly positive. And then this is just reminding you of a little trick, is that if your inequality points the wrong way, like here I have y has to be less than 34. So then you think, okay, I'll just move 34 over to that side. So y minus 34 has to be less than 0. Notice that my inequality now is strictly negative. If you want to flip the sign of the inequality, you remember if you just multiply both sides by minus 1, it will flip this sign. So then this becomes 34 minus y is greater than 0. So it's just a reminder that if you ever arrive at a strictly negative inequality, you can just multiply both sides by minus 1, which flips the inequality sign to be greater than. Okay. So that is basically constraints. Okay. So we can do constraints in minimization. We can do constraints in n dimensions. And now we're going to just I'm just going to blow through this example. I think if you want to study this in more depth, you can. This is a good, complete example. But I'm just going to show you a non-convex optimization with constraints. This is just kind of a fun example. It's springtime. Okay, so here we have a flower, all right? And here I have a bee. And the bee wants to land on the flower. And the bee wants to minimize how far it has to travel. So let's find the point on the flower that's as close as possible for the bee to land. All right, so there's the setup. Now, uh, like I said, I'm going to kind of skip over some of the details here. This is the first example we've seen in lecture of a polar coordinate system. So I think this is kind of an interesting example to study because it shows you how to plot and work with polar coordinates. This is also an interesting example to study because it's a non-trivial example, right? Like some of the examples we have in here are pretty straightforward. This one is sort of complex. There's a little bit of work that needs to be done, okay? But I think we're going to give a nice, fun, high-level view of this. So I have a bee landing on a flower, okay? Uh-oh, why can't I scroll up? All right, so I want to find a point as close as possible. So the first thing I need to do is I need to set up my constraint. So I need to say that we stay on this flower, right? Now I'm going to actually solve this problem in Cartesian coordinates. This equation for the flower is defined in polar coordinates. Why is it defined in polar coordinates? Because this is not possible to define in Cartesian coordinates, right? This is not a valid function, right? It doesn't pass the, the vertical line test, okay? So to check my constraint, I need to convert my Cartesian coordinates into polar and make sure it lies on my pretty flower function. Okay. So remember that constraints, like all functions we work with minimization and stuff, they take in one argument. So I'm going to take in s, and s is going to be in Cartesian because I'm going to solve this problem in Cartesian coordinates. So s contains two elements, my x and my y. So I do a coordinate transformation to r and theta. And then here is my function for the flower. And I'm just saying that it needs to be equal to 0. So my function for the flower is r equals this expression. So to make it a 0 expression, I move r to the other side. So I'm saying that this expression needs to equal 0. So for the point xy to lie in the flower, this expression needs to equal 0. And you may be wondering, like, hey, how can you do a conversion from Cartesian, to polar, and then how do you know you're on the top or the bottom of the flower? Well, it doesn't matter for the fact that it equals 0, so it doesn't really matter. I don't need to get a clean conversion to the top or the bottom of the flower to know that I'm on it. Okay, so this is just me testing out the constraint. So I have a constraint, so I've defined, if this constraint is 0, it tells me that I'm lying on the flower. Then I again have a distance function, and then I'm saying, okay, if you have a point x or s, right, then if I compute the distance from that point to the point 1, 2, that tells me how close I am to that dot in my plot. Okay, so it's actually very similar to the circle problem. It's just we have a more complex constraint. And now here's the tricky part, is that this is non-convex, right? Like you saw the flower, the shape of the flower is very non-convex. So this is a non-convex problem, so I have to use basin hopping. Now with basin hopping, I can't just pass in constraints directly. I have to wrap them into something called the minimizer keyword args. So like we discussed from Hao's question, basin hopping calls the minimize function. So if I want to tell the minimize function something like, please obey these constraints, I have to pass in a dictionary, and that dictionary contains the arguments that I want to pass to the minimizer. So if I want to constrain, I want to tell the minimizer, here are some constraints. So I need to make a dictionary whose key is constraints, because that's the named function argument I want to set. I want constraints to be equal to my constraints, which is a dictionary I've created here, which is just like the dictionary we saw before. So I basically need to have a dictionary within a dictionary to get minimizer to listen to me. So I tell basin hopping, please pass these arguments to the minimize function. And recall, we want the minimize function to take in the argument constraints to be equal to my dictionary. So that's what this first dictionary does. And then here I'm actually specifying my constraint. My constraint is an equality constraint that my circle constraint needs to be equal to 0, which forces the xy values to lie on the circle. So I run it, and it works. And it turns out that this orange point here is the closest point on the flower to the red dot. So the bee, when it comes down to land on the spring flower, it needs to land right there to minimize how much flying time it has. All right. So again, this was just an example of basin hopping. Basin hopping can do bounded or constraints, but you have to pass them through this minimizer quargs object, which basically says, you have to wrap things in a dictionary. Phew. All right. So that is and if you take numerical methods at another university or from another professor, you will never do something as complicated as bounded, constrained, non-convex optimization. But thanks to Python, it's actually not too crazy to do. Like, this problem would have been like a really challenging research kind of question maybe 10 years ago or 15 years ago, but now it's pretty straightforward actually to solve this in Python with just a few lines of code. So I think this really demonstrates the power and the utility of using Python for numerical methods. Are there any questions on this example? Great, we got some wows in the chat. Excellent. It's a pretty impressive method. Okay, so that's all I want to cover for optimization. So we saw on Thursday in lecture 1, we saw how to do root finding and minimization and maximization. And then in this lecture, we saw how to add bounds or constraints and how we can treat non-convex optimization by using basin hopping. One thing I didn't mention in too much detail here is that remember with this basin hopping, we have to pass in how many iterations we're going to do. And there's no good way to know how many iterations to do, right? Like you could do 10, but maybe if you do 100, you find another lower local minima. Maybe if you do 1,000, you find another local minima. So what is the rule of thumb? How many iters should you do? What I would say is do 1,000 and do 100. If after going from 100 to 1,000 you saw a pretty big difference, then try going to 5,000. Then if you see a big difference from 1,000 to 5,000, do 10,000. And then once you stop seeing a difference, then you can be kind of, you're heuristically sure. That's a heuristic that you have done enough work. Okay, but there is no, this is an open research problem. How do you solve non-convex optimization? How do you know when you have explored enough local minima? And something I haven't mentioned, but just kind of goes without saying, is that this basin hopping method only really works maybe to 4 or 5 dimensions. I wouldn't trust it in 5 dimensions. If you're doing a very large dimensional non-convex optimization, please apply to our PhD program. This is a great open area of research, and I do research on this, so would love to have you, but otherwise don't use this for large dimensional non-convex optimization. Okay, are there any questions on optimization? All right, great. So I'm going to stop recording.